Hello, good afternoon. Today we are presenting on the platform International Symposium on Renewable Energy and Sustainability, which is organized by Ibero-Americana University and Instituto de Energías Renovables de la UNAM. We are taking the topic on production of functional and reusable biodiesel-derived glycerol-based carbon for the synthesis of oxygenated fuel additives. This paper was written, propagated by myself, Patrick Okoye, and Dr. Sebastian Patiyamaton. The event of the awareness of the adverse effect of fossil fuel has actually propagated interest in the direction of renewable energy. Renewable energy has aspects of solar, the wind, the geothermal, and the biomass energy. This biomass energy is quite attractive because of its abundance, and it can be converted into fuel directly and can at times be sourced and used directly. So, the production of biodiesel from biomass has been a notable and remarkable progress towards production of energy from biomass, as well as challenge due to some problems of one, the feedstock. However, these problems of feedstock could be averted or solved by tracking the feedstock that are abundant to each country and then utilizing it directly. The production of biomass is primarily and mainly, of biodiesel is primarily and mainly towards uh, transesterification reaction. And this transesterification reaction uses vegetable oil, animals, and waste, and an alcohol, usually methanol, and a catalyst to produce biodiesel and glycerol. For every 100 gram of biodiesel produced, about 10 grams of glycerol is produced, which makes it an abundant material that can and should be reused to propagate or to boost the viability of biodiesel. Glycerol as well is a platform chemical with various advantages. In fact, it can be used for many fine chemical production and also polymer production. However, the problem with glycerol is the in situ impurities. For instance, methanol, which is a low boiling point material, so disposal challenges are always encountered. And this crude glycerol obtained from biodiesel products is very cheap compared to the refined one. Hence, one has to find a need or a way to upgrade this glycerol or to utilize it directly. Various techniques has been assessed in the past, including acetylation reaction and carboxylation reaction. These techniques produce one form of chemical or the other. Today, we will base our talk on acetylation reaction. This pathway generates monoacetylglycerol, triacetylglycerol, and triacetylglycerol. The diacetyl and triacetylglycerol acetylglycerol are oxygenated compounds. These oxygenated compounds can be used as a cetane booster in our fuel directly. But the pathway of acetylation reaction with acetic acid is thermodynamically resisted because of the in situ water generated. However, production of catalysts that are either resistant to this in situ water or the use of the Dean stack to evacuate the in situ water could promote the acetylation pathway. Hence, heterogeneous catalyst has been the favorite of several industry because it offers several advantages such as high reusability, less corrosive to reactor and pipeline, easy and faster to separate from reaction mixture against homogeneous catalysts that are very corrosive and its reusability is very difficult. So in this topic, we thought of production of Bronsted acid materials from crude glycerol, because the idea of using crude glycerol to also produce catalyst and then use this same catalyst to promote the reaction of glycerol acetylation pathway is a net zero um, it's a net zero work, so that these two materials can as well be used complementarily as a catalyst and as a reactant. In this work, crude glycerol of around 80% purity was partially sulfonated and phosphonated using phosphoric acid and sulfuric acid. Thereafter, the material was heated at 100 degrees to dehydrate it and achieve partial sulfonation and phosphonation until a solid black tar was obtained. The tar was thermally treated in a hydrothermal carbonization reactor at 300 degrees for 3 hours. The carbon was obtained and then washed to remove the excess acid on the surface of the material. These material, respectively, the sulfonated glycerol-based carbon and phosphonated glycerol-based carbon, was applied to propagate the acetylation reaction. And the target is to obtain at least more than 70% yield of these combined compounds, and the reusability to have at least five reusability, and the material to be stable in polar media without rapid deactivation. So, assessing this material porosity and surface area, we found that we were able to obtain enhanced porosity and also a surface area greater than materials that are not treated with hydrothermal synthesis. When it has been reported before that ordinary treatment of sulfuric acid with glycerol based carbon produces material with surface area less than 1 meter square per gram and without any pore. But in this scenario, we obtain pore which could enhance mass transport in and out of the sites of our material. Also, we have seen evidently that some elements of sulfur and phosphorus was incorporated and the acidity was really enhanced. So, the high density of the acid is due to relatively low carbonization temperature. And also these materials that we used has more Bronsted acid site, which is attributed to mainly the sulfonic acid group species and the phosphonic group species. Also, the isotope here is type 4 isotope with H2 hysteresis, showing that it is typical of mesoporous material. The effects of reaction condition shows that the molar ratio, reaction temperature, and the reaction time contributed immensely to propagation of this reaction. In fact, we can see vividly that as molar ratio increases from 1 to 4, the yield of triacetylglycerol and diacetylglycerol, and as well the conversion is almost constant. It should be noted that the conversion of this in the acetylation reaction is usually independent of the yield of the triacetyl and diacetylglycerol, because the acetylation pathway is a stepwise reaction path, such that even the production of monoacetylglycerol, which is the first compound before the di and triacetylglycerol, could result in conversion of 100%. So, from our discussion, we could find that higher temperature as well increases the yield. However, at a point around 120 degrees Celsius, we found that a slight decrease in diacetylglycerol and triacetylglycerol was envisaged. And the reason is because of possible side reaction formation, which is usually encountered in this experiment. The catalyst produced evidently shows that it could tolerate water and propagate thermodynamic resistant acetylation reaction. The best condition that were obtained was 110 degrees Celsius, 3-hour reaction time, and molar ratio of 3 to obtain over 70% diacetyl and triacetyl uh, glycerol for the both catalysts evaluated. And the reusability of this study shows that the catalyst is robust in aqueous media. Hence, the catalyst could be reused for 5 times without rapid deactivation. Hence, we conclude that porous carbon based material could be produced from crude glycerol via hydrothermal treatment. And if we want to increase the surface area, we can do higher thermal treatment to obtain even higher surface area. Secondly, the catalyst promoted very high products of acetylation reaction, which is diacetyl and triacetyl glycerol, respectively. Third, the catalyst could be reused for 5 times without serious deactivation. However, the, there is a slight decrease in the acidity of the material, showing that there is a slight leaching of the acid. This leaching could be stabilized by producing nano carbon material with enough Bronsted acid or anchoring this material on another support to increase the stability. Hence, we recommend that sulfonic acid group should be increased and reaction time should be prolonged to achieve even higher triacetyl glycerol and diacetyl glycerol. Thank you for giving us the chance to make this talk. Thank you very much.